All right, so for these particular limits, we're going to start with direct substitution. Okay, and then depending on what you get out, like this, that might tell us that we have to do some more work. Okay, so if we do direct substitution and we plug the limit into number 1, what would we do? Or what would we get? Okay, so if you plug 0 and you get 0 over 0, right? Okay, so anytime you get 0 over 0, that means that there is actually a limit value. Okay, so what you're going to have to do is you're going to go back to the function and simplify it algebraically. Okay, so if I go back to x over x plus 1, what do you notice? You can take the x out, so an x can cancel with another x, and what would be left over? 1 over x plus 1. Okay, so then at that point, now I'm going to do it again and do my limit as x approaches 0, and I'm going to plug 0 into this new function. Okay, so if I do that, I would get, everybody okay with 1 over 1? I don't plug a new value in, I simplify the function and then plug it in again. The 0.
Wouldn't that be like removable?
Yes, good point. Okay, so let's talk about that while we're doing this. Okay, so because I canceled the x, there would be a removable discontinuity at which value? Which x value would make that 0? Okay, so you can say there's a removable discontinuity, or you can even say whole. What?
How come you know there's a hole there?
Because when we canceled this out, x over x, that created a hole.
Oh.
1 over 1 is 1. How I got 1 over 1?
I got 1 over x.
I just plugged 0 into this.
Oh.
Okay, ready for number 2?
Wait, what?
No.
I thought x equals 1 now.
Yeah.
Why'd you say removable discontinuity?
We're just making an extra statement, so maybe I won't circle that because apparently that's confusing. That's not part of the question, but we're just making an observation that there happens to be a hole also at x equals 0, because that's good information for us to know in case they ask us about holes later on, right? And discontinuities, because there's more continuity stuff here. Okay? All right, so what about number 2? If I plug 2 in, what do I get?
Don't you have to plug in like 1.9 or something?
0 over 0.
No, I plug it straight in. It's direct substitution. Okay, so if I plug 2 in, I get 0 over 0. Is everybody okay with that? Okay, so if I get 0 over 0, what do I have to do?
Cancel.
Cancel, and I'm going to have to factor. I'm going to have to play with this a little bit in order to factor it. Okay, so which of those two quantities can be factored?
X minus 2 x plus 2.
Okay, so the bottom can be rewritten. So I would have the limit as x approaches 2.
1 over x plus
2. Okay, so those would cancel, so I'd now be able to take the limit as x approaches 2 of 1 over 2 plus 2, which is 1 over 4. Okay, so that's the answer. Where does there happen to be a hole in this particular example?
We're going to have to figure that out.
No.
What?
They might, yeah. Not on this question, though. Okay, so where would the hole be? What quantity did it cancel out? Okay, so what value would make x minus 2 0? 2. So there is a hole at x equals 2. Okay, so that's just a little extra info. The 1/4 is what the answer is to the question. The limit of the function is 1/4. Okay, what about number 3? What happens if I plug 1 in? You what? Are you sure?
Do.
Yeah, you do. Just wondering if you actually tested it. But yeah, you do. You get 0 over 0. So what does that tell you? You have to factor it. Do you guys remember how to factor difference of cubes? Okay, so here's a little thing you might write down, a difference of cubes. This also works for the sum of cubes. I'll write both of them down at the very top here. If you have a cubed plus b cubed, that's a sum of cubes. So usually when you see this, you have like an x cubed plus 8 or something. Okay, factors into a plus b, and then a squared minus ab plus b squared. Okay, so if we have a difference of cubes, which we do have, oops, that would factor into a minus b, a squared plus ab plus b squared. Okay, so that's something you might hold on to. You might see it again. You probably will see it again. Okay, so if I take that information and now apply it to x cubed minus 1, what does x cubed minus 1 factor to? What is my a value and what is my b value? Okay, so how did they create x cubed? What did they cube to get x cubed? X. Okay, so the a value is x. Okay, I'll write this right here. A is x. Okay, what's the b value? What did they cube to create 1? What times what equals 1? 1. Okay, so now I can use my difference of cubes little formula up there and just really plug it in. So what's my first quantity? So x minus 1. Then what? It says a squared plus a times b, so what's x times 1? And what's 1 squared? Okay, so what do you notice? Okay, the x plus 1's cancel, so now we can do the limit as x approaches 1 of x squared plus 1 x plus 1. So now we would just plug 1 in. So 1 squared plus 1 is 3. Okay, so the limit for that question is 3. FYI, where would the whole be? At 1, right? So there is a whole at x equals 1. Okay. Okay, so moving on to question number 4. If you plug 1 in, what do you get? 0, just straight up 0? Because that's a number. That's an answer. 0 over 0. Now that's a problem. Okay, so if I have 0 over 0, I would try and factor, or I have to do some kind of algebra. Okay, this particular question involves a square root. Does anybody remember how you manipulate this particular function? It's kind of close though. You what? You don't square the whole thing. Okay, so we're going to multiply by something. Okay, but when we multiply, remember that we can't just square it, or we're changing the whole equation. If I square something, then it's changing its value. But I'm going to multiply by the value of 1, but I'm going to multiply by the conjugate of the square root. Okay, so the conjugate of the square root piece, what's the conjugate? Very good. Okay, so I'm going to multiply by the square root of x plus 1 on the top and on the bottom. Remember, I'm not changing the value of this function. Okay, so when I FOIL on the top, what's the square root of x times x? X. Can I go ahead and know that the conjugates, the middle two terms, cancel out? You guys remember that? Okay, and then I can just do the last two together. So it's -1 times +1. -1. Okay, now on the bottom, do not FOIL. Never, ever, ever FOIL the bottom when you're dealing with limits. Okay, because look at what happens. What do you see? Whoops. You don't get the same thing, right? The x minus 1's cancel. So now we're left with 1 over the square root of x plus 1. Okay, and now we can plug in our limit value. So we'll end up with 1 over the square root of 1 plus 1, which is 1/2. Okay. Going back to the original, where was my hole at? Okay, so notice that we did end up manipulating it in the x minus 1, which was a point of discontinuity. There is a hole in the graph at that spot. So FYI, there's a hole at x equals 1. Okay, it's a point of discontinuity. Yes. Yes. When you're dealing with limits, yes. Okay. What about number 5?
Can you just plug in 2 still?
Okay, we are gonna plug in 0. Or not 2. I don't know why I just said 0. 2 is what I meant to say. We're gonna start by plugging in 2, but what is different initially that you guys notice about this? It's from the right. Okay, so we need to be mindful about what happens on this graph. Okay, if I plug in 2, I would get 2 over 2 minus 2, which is 2 over 0. What does this tell me? This tells me something very important right now. There's a vertical asymptote. Okay, so holes are created when you get 0 over 0. Holes are created. But if you get a number over 0, that's a vertical asymptote. I would totally write that down. 0 over 0, whoops. Oh my gosh. Hole. But if you get a number, I'm going to use n over 0, that implies a vertical asymptote. Okay, a vertical asymptote means that the function is either going up towards infinity or it's going down towards negative infinity. Okay, so if we've got a vertical asymptote, at this point I can say, okay, I know the answer is either infinity or it's negative infinity. How am I going to choose if I don't have a calculator to check it on? How would I do this algebraically? How about let's pick a number that's on the right of 2. Very close to right, or very close to 2. So give me a really, really, really close number to 2 that's on the right of it. 2.1. Okay, let's get really close. I think 3 could be potentially too far away. We want to be really close. So let's use 2.1 and see what happens. Okay, so we know that it's either going up to positive infinity, positive numbers, or it's going down to negative infinity, where there's negative numbers. Okay, so if I do this, I get 2.1 over 0.1. Is this a positive number or a negative number? It's a positive number. Okay, so that tells me that this function is going up to positive infinity. Okay, so I would say from the right, this is going to positive infinity. Okay, now it is possible for you to answer does not exist because infinite limits are technically not finite. I can't give you an infinite amount of something, so they're arguably non-existent.
So as soon as we get a bigger number on top.
A bigger number on top? Well, you have to know if you have a positive or a positive. Because if you had a positive number over a negative number, that would be a negative. Go to negative infinity. Okay. So by the way, if you did graph this function, and I think you could potentially graph it, it has a vertical asymptote where?
2.
At 2, right?
Or
It also has a horizontal asymptote. Okay, do you guys remember the 3 cases of horizontal asymptotes? Okay, so you're looking at the biggest exponent, so we're looking at the x over the x. If it's bigger on the top, it has a slant asymptote. If it's bigger on the bottom, it has an asymptote at 0. If they're the same, then you use the coefficients that are in front of them. Okay, so this scenario would be the same because it's an x over x. So what's the values that are in front of those x's? 1. So there happens to be a horizontal asymptote at 1. Okay, and then you guys remember what it looks like? What's its parent function? Remember the hourglass? Okay. Okay, moving on. Oh, I have to go to page 2, I guess. Is that what you guys have next? Is this right? 6? Okay. So number 6 says discuss the continuity. Okay, so now we're deciding is there holes, jumps, asymptotes, and we are saying specifically is it a removable discontinuity, is it a non-removable discontinuity, and where specifically. Okay, so in order to discuss continuity, we need to talk about each of the pieces when we have a piecewise function. Okay, so if we start on the top piece, is there any types of discontinuity? How did you know there was a hole? Did you put 3 into the top 2 and say, oh, it's 0 over 0? Okay, absolutely, that is perfect. Okay, the other way you could have done this is you could have factored the top part. So x squared minus 2x minus 3, what does that factor into? X minus 3 and x plus 1. So if you have that over x minus 3, they cancel. Okay, so this means you have a hole, which is what kinds of, what value makes the x minus 3 0? 3, right? Okay, so you have a hole at 3. What type of discontinuity is that? Removable or non-removable? Removable. Okay. So, but notice that the second piece, and notice where our interval happened. Okay, but it says where x is not 3. Okay, so on our original top function, there is a hole. Otherwise, it is completely continuous. So the only way for this whole function to be continuous is if the second piece existed right at the same spot where that line would continue. Okay, so do you guys know what this function looks like? Do you know what this function looks like? It's exactly the same function. One just happens to have a hole at 3. If you were going to graph x plus 1, you would say, oh, that's a linear function that's up 1 with a slope of 1 over 1. Okay, and then what happens is when x is 3, I'm going to draw a hole in the graph. Right there. Otherwise, it's a straight line. It's going to look exactly the same on the calculator as x plus 1. Okay, so is 5 the corresponding y value right there? And that hole Is that one, the second piece, going to fill in the hole? Is that going to go right there? How would we find out? We can do it algebraically. We can probably even look at the graph and say, it's close. Okay, so all we have to do algebraically, okay, is if I take x plus 1, my function fx plus 1, and we're specifically looking at the x value of 3, so what do you think I would do? Plug in 3. So if I plug in 3, do I get the same number as this right here? No. Okay, so 5 would exist. This would be at 4. My drawing is not beautiful. The hole would be, or that little spot would be there.
Is that hole supposed to be at 3?
Yeah, the hole is at 3. The x value of 3. Okay, does that make sense how you draw those functions with the holes? They're always easier than they look. Okay, so number 7, they ask us to find the value of a, and they specifically say that this function is continuous. Okay, so if we know that this is continuous and we have a piecewise function, that means on the top, 3x squared plus a looks like what? A parabola. So we got this parabola, and then when x is 2, it stops. And then we got x minus 3, which looks like a linear function, and then it goes up. And for this function to be continuous, they need to meet at the exact same spot. Okay, so we are going to use this right here. We're going to start with this and try to figure out the a. So we're first going to say, okay, well, if I plug 2 into the x value, I will know what the corresponding y value is that I need for the top piece to be. Okay, so if I have 2 minus 3, I get negative 1, right? Yes? No? You guys paying attention? Okay, so now I know that the top function needs to have a y value at negative 1 when I put 2 in. Okay, so I'm going to go to the second piece and I'm going to say, well, I need negative 1 to equal 2, or excuse me, that's a 3. 3 times 2 squared plus a. Does that make sense what I'm doing there?
Why does it have to equal the y value?
Because for it to be a continuous function, so remember I have this parabola and it stops at 2. Well, I need the line to start at the same spot, the same x and y that the parabola left off at. Okay, we know what the x value is. We need to figure out what the y value is. We know now that the y value is negative 1, so we need to figure out the a value that makes that top piece true. Okay, so if I just solve that, I would have, let's see, 4 times 3. So a is equal to negative 13. I got it from the bottom piece. Okay, so I took x minus 2 and I simply plugged the x value that they separated at. So I'm looking at right here. See where they separate? Okay, so I want them to separate at the same exact y value. Okay, so I plugged 2 into the x to figure out what the y value would be on that first linear function. Okay, so the y value would be negative 1. So once I know that, I can say, oh, I need the negative 1 to be the y value of the top piece, the x squared. And I know the x value is 2. Okay. All right, guys, we got 2 left. We're almost done. Oh, no, I know. We don't. 4 left. Okay, number 8. How do I use a calculator to find limits?
Just grab it and see what it costs.
Uh-huh. So if we pull up our Webbit, come on, Webbit. There it is. Okay, so, oh, I got 2 rabbits. I'm going to start by graphing it, right? Because we want to see what this looks like. I'm going to use the fraction button so it looks just like the other one. So we got x cubed minus 3x squared plus x plus 2. On the bottom, it's almost the same. X cubed minus 2x squared minus x plus 2. Okay, so we're looking at the x value of 1. Anybody want to take a stab at that one? Okay, so you guys see the vertical asymptote is existing right there? And the x value is 1. That is a doozy. So that means it was completely factorable. So it does not exist. Aren't you glad you could use a calculator for that? Yeah, that one just does not exist. Boom, done. See how there's the vertical asymptote right here? Can you see my little cursor? No, you can't. So when x is 1, right here, there's vertical asymptote. Doing the limit, yep. If it asked you from the left or from the right, you would either say if it was from the left, it would go to positive infinity, from the right, it goes to negative infinity. But since it's just limit and they don't go to the same place, it doesn't exist. Asymptote. Graffiti. Isn't it very legible? All right, so for B, they give us the same function and ask us now to find it 2. So this one, I'm going to actually have the calculator. It would just be plugging in the value of 2. But instead of doing it all in my home window, I'm just going to hit second trace and tell it what value I want it to plug in. So if I plug in 2, it's going to pop out, so again, we've got a hole at 2. Okay, so how are we going to figure this out?
Go to 2.1.
Okay, so we can trace it and we can get really close to it. So we could go 2.1 and plug something in really close. We know that the function looks continuous, so it exists. So let's get really close. Okay, so 0.384, I bet we could even get a little closer to 2 than that, right?
0.1.
What? 2.01? How about like, did you guys say that in unison? That's so cute. 2.0001.
Oh gosh. I'm just gonna say 3.
So would you maybe agree that it would be 0.333 if we are rounding to the nearest third decimal place?
I don't know.
I'm going with 0.333. I like that one.
Yeah, I just went 3.
Why can't we do it?
Probably was 1/3. What's that?
Why can't we do it exactly?
Because it's a hole. It doesn't exist at 2.
There's a hole there?
There's a hole. Because if you type it in and it said, so see what happened when I did that? So I couldn't see the hole visually, but if I typed 2 in, there was no answer that came out. So that means there's a hole there.
So what do you write?
So then I used a number that was really close to 2. So I used 0.00001, and then I got out 0.333333888, which I'm going to call 0.3333.
So you wouldn't write does not exist because it doesn't
Right,
say
it
what
does
value.
exist. Because if you look at the graph, it is clearly going to the same place from the left to the right. So if this is 2, it's like right here at that spot. Like it looks continuous. Okay, guys, we're almost done. Hang in there. Okay, so this last one is called the intermediate value theorem. Okay, so the whole idea of this is if you have a continuous function, okay, so if your function is continuous on whatever interval they give to you, that is a specific piece of this. It has to be between a given interval. Then if you plug in the a value and you plug in the b value, then the corresponding limit must be somewhere in between those values. Okay, so if I say, yes, it's continuous, if I plug in a, I got 2 for my y value. If I plugged in b, I got 8, then I know that the limit is somewhere between 2 and 8. Right? No. On which one? If it's asking you at the point of discontinuity, if it's a jump or an asymptote, but doesn't exist. Okay, so you ready to do A? Okay, so the first thing I'm going to do is decide whether or not my given function is continuous between 0 and 5. So is x squared minus x continuous? And in fact is always continuous. So we can say f of x is continuous on the interval 0 to 5. Okay, so if there was a point of discontinuity in that spot, I can't use this theorem and I would just be up a creek. Okay, but since we can now say, all right, well, step 2, now I'm going to plug in the smaller value into my function, and then I'm going to plug the bigger value into the function and see what I get. Okay, so I have 0 as the lower, so that would be 0 squared minus 0, which is 0. And then if I plug in 5, I would have 5 squared minus 5, which is 25 minus 5, which is 20. Okay, so now we can say, okay, so I know that as long as my C value, which happens to be, what's my C value in this case? 12. Since 12 lies between 0 and 20, then there must be something. So that's all we can really conclude at that spot. So we can say by the intermediate value theorem, it guarantees, how do you spell guarantees? Guarantees a C value in 0, 5 such that f of C is equal to 12. Okay, so in this particular case, you're not able to actually find it. Well, you could find it, but I guess we'll do that in the next problem. All we know is that it does exist. So you can use the intermediate value theorem. Okay, so what about for B? What's my first step on B? To decide if I can use the intermediate value theorem. Right, so is it continuous? It is not continuous at 2, right? So for B, you see a problem? So g of x is not continuous at x equals 2, which is in the interval of 0 to 3. So no intermediate value theorem. So you can't use the intermediate value theorem to solve this one. You just have to stop and say, I can't do it. It's not possible. It's not continuous. Okay, so for 10, now they're actually asking you to find the C value. Okay, so this is very similar to what we did with the continuity thing and finding the C value up above. Okay, so if we know that this function is continuous and we know that the corresponding y value at whatever c it is 12, okay, we're going to say, well, the y value is 12 of our function, and all we have to do is now figure out what the x value is, which is our c. See how I set that up? Because I know the y. So, yep, I got to set it equal to 0. So I have 0 equals x squared minus x minus 12. Easy method says, which two numbers multiply to negative 12 and add to negative 1? Negative 4, positive 3. So the two values that make this statement true are 4 and negative 3. Okay, at this point I'm going to use my interval, 0, 5. So which of those exists between 0 and 5? Only 4, right? So that means my c value is 4. Good? You guys look ready to roll.
Wait, why?
Because it's not in the interval between 0 and 5. Okay. All right, so this is what we're going to do. I'm going to give you the assignment. I want you to go 1 through 26. Okay, those are your problems that I want you to do for Friday.
She wants us to